I've been doing this for 35 years. Richard Schwartz reminded me that Edison, in one of his main inventions, was the electrical chair. Can you imagine the first guy they applied this to going, great. They had to use AC, would have killed them if they used DC current instead. Anyway, so, ooh. Root seeking, along with other numerical analysis techniques like linear algebra, optimization, interpolation, integration, all that stuff, are the foundation of legacy numerical analysis. And this is yet another twist on Newton's method, and Sigmund Freud here justifying, he said this is becoming obsessive compulsive behavior, and for once I say he's right. Yeah. Most of us should know the basic Newton's method to find the root of a function f of x equals 0. And ever since the HP65 came in, even with the standard packs, they had implemented Newton's method. And you basically take a guess for the root and refine it using the equation here, you see. And it's x minus the function value at x over the slope at x. Now, if you don't have CAS, so until recently, we had to approximate the slope. And there are, we use difference methods, and there are several of them. There are 3 popular difference methods. The one, and that's the most popular one, is the forward difference method, where you approximate the slope using f of x plus h minus f of x all over h. H is a small increment value. The backward difference is very similar, where it's the slope is f of x minus f of x minus h all over h. And the central difference approximation uses f of x plus h minus f of x minus h all over 2h, h always being a small increment. Now the last formula is more accurate than the first 2. Now the typical option I've done for years and years and years is to select one of those 3. Mine, the favorite, is the first one. So the first 2 approximations require 2 function evaluations per iteration. But the third one, that's more accurate, requires 3 function evaluations per iteration. Now, there's a little debate. Is it the iterations that count more or the function calls? My opinion, it's the function calls, especially if you're using a vintage calculator, and you know, and especially if your function is like a series approximation, then you will begin to see how slow it is using more function calls per iteration. If you're using a fast computer like Excel or MATLAB or Mathematica, probably you won't notice. Unless you're doing this a million times, then yeah, you will see the difference again. Now the new algorithm says, rather than choosing one of these 3 approximate methods, let's use them all. And the trick is, so the first variant is, okay, we start an iteration, we have a guess and the function value. And we use each approximation to get 3 interim refinement for the guess of the root, and then calculate the function values at each of these the roots, and then perform inverse Lagrangian interpolation to get a better refinement for the root. The second variant of this method is similar, but instead of having just these 3, remember when we started the iteration we had x and f of x, and that comes free, there's no additional calculations needed. So we throw in that point too, and we have an inverse Lagrangian interpolation with 4 points, even better. The third variant is sort of similar to the first method, but skips the inverse interpolation method and uses a weighted averaging, giving more weight to the central difference because it's a little bit more accurate, like maybe weight of 2 and then 1 for each and divide by 4. Here's a Visual Basic application code, simple code using Excel. So we start by I have a guess in cell B1, and I store it in X guess. I set up my iteration counter to 1, and then I evaluate the function value here. S of X is a string, so I can just type in, I don't have to hard code the function, I can enter it in the spreadsheet, and I can then test varieties of functions without hard coding it every time. And then I start my loop here, and I store the current guess at the top of the loop into X last, so I can use it later on for comparisons purposes. I calculate the increment here, H, based on X guess, and then I calculate the values for X plus H and X minus H, and then I calculate the 3 interim refinements for the guesses here. And then this for loop here calculates the function values at these interim guesses. Then I test here, B-exit, that no two values in the Y array are equal. That can happen if I'm actually very close to the root, and that will cause problems in the inverse. That will cause a runtime error in the inverse interpolation. So if B-exit is true, it means I'm basically on my way out of the whole iteration. If it's false, then I perform the inverse Lagrangian interpolation to calculate xint as the refined guess at that iteration, and store it into xguess, and then increment the loop counter. If B-exit is true, I jump here and I take x of 2, that's the one I got from the central difference, the better approximation, and store it into xguess. And then, of course, I display the interim values, as I will show you later on in an example. Recalculate f of x again, and display that, and then take the difference between the new guess for the root minus x last, which was the value at the top of the iteration. And then I have here a clause to say when do I stop. So if the absolute value of this difference is less than the root tolerance, or if k exceeds a number, in this case I put 100, you can put less, more, whatever, or if B-exit flag is true, or this is an optional also, if the absolute value of the function is less than a function tolerance value. Sometimes I use it, sometimes I don't, depends on the nature of the application. And then I finally calculate the number of function calls so I can see what's happening. I'm going to present 3 examples, and in each example I have 2 sets of slides and then a textual analysis of the results. In each, I have 3 sets here. Each set has 2 columns. I show you the value of the root, guess for the root, and then the function value. Now I start with my favorite function, e to the x minus 3x squared, give it a high guess value of 6, and a tolerance for the root of 10 to the minus 7, and function tolerance value of 10 to the minus 10. It has to be low, otherwise you will exit a little bit prematurely with less accuracy. This one, the first 2 columns is for the forward difference method, which I will use as my default baseline to compare everything else with. That's the one I personally use and a lot of people use more frequently. This is the central difference. As you can see, it has more iterations, but more function calls, but fewer iterations. And then this is the inverse Lagrangian method with 3 points. Actually has fewer function calls and fewer iterations. Second screen also same function, and now I have the inverse Lagrangian with 4 points. Again, fewer function calls and fewer iterations. And then this is the average weight, and I actually have more function calls, but fewer iterations. So
are those all roots? All of those?
Yeah. One column is roots, and the other one is the function value at these. So, okay, now we compare. The 3-point and 4-point inverse interpolation require 3 iterations and 18 function calls, and that's the best in the set. The 3-point average method requires 7 iterations and 21 function calls. Not really so great. The central difference method requires 8 iterations and 24 function calls. That's the highest. So sometimes when I would play with the subtract, maybe I should have used the central difference all along. No, not really. Sticking to the forward difference was actually paid off here because I only have 10 iterations and 20 function calls. So far the inverse interpolation methods, the 3 and 4 points look very good. Second example, I have a function x minus the natural log of x to the 4th with the initial guess of 9 and tolerance of 10 to the minus 7 and function tolerance of 10 to the minus 10. And it solves it. This is the forward difference. This is the central difference. A little bit more function calls, but fewer iterations. Here is the inverse, 3-point inverse interpolation. 1 iteration and 6 function calls. And when I compare that with the 4-point inverse interpolation, again, 1 iteration gets me there at 6 function calls. And the weighted average, I require actually more function calls, but 1 less iteration. Again, here we see that the 3-point and 4-point inverse interpolation method did real well. They required 1 iteration and 6 function calls. The 3-point average was not that great. It required 3 iterations, but 9 function calls. And the same thing can be said for the central difference, same statistics. And the forward difference had 4 iterations, but 8 function calls. So it's not bad. The last example, I have a simple polynomials with roots of 1, 2, minus 1, and minus 2. And I give an initial guess of 10. So I'm going to zoom on the root x equals 2. Again, I'm using the same tolerances as before. This is the forward difference. And you have 14 iterations, 28 function calls. This is the central difference. Oh, sorry. More function calls, but fewer iterations. And then the inverse Lagrangian with 3 points, I have more function calls, but fewer iterations. And with the 4-point inverse, I have actually fewer function calls and fewer iterations. The weighted average actually required more function calls, but fewer iterations than our standard baseline. So now, the winner is the 4-point interpolation method with only 3 iterations and 24 function calls compared to 5 iterations and 30 function calls. The 3-point weighted average had 11 iterations and 33 function calls. Same thing can be said for the central difference. And the forward difference has 14 iterations, the most, and 28 function calls, which was not bad. Here, the 4-point inverse clearly is the winner. And remember, you're just doing a little bit more loop in the one more loop in the inverse interpolation thing. But the fourth point you're using comes at no extra cost because it was already there at the beginning of the iteration. So, thank you.
Question?
Yes.
So on the, I'm trying to relate to the tolerance that you choose. Is that just a function of the numerical analysis you're doing, or is it actually relate to what you're trying to measure? Because it seems like it's very, very small, right? You're at the minus 10 to the minus 10, right?
The function value, yes.
Right.
You can do 10 to the minus 8 maybe. And it depends also on the function, the sensitivity. If you're getting like if the function returns really huge values and you're trying to zero it, then you can be more forgiving. And the same thing is true if your answer is, for example, you're calculating temperature in the thousands and all that.
Right.
Your tolerance could be 0.01
Right.
because, you know.
You may not care, right?
So, yeah, some people use a percentage difference, you know. The only thing is, the problem is if your answer is 0, you'll be in trouble. And some people have found, I think on a previous HHC, I discovered, I remember one talk about tricks, and that was one of the tricks is to add an epsilon, so that if your root is 0, you don't divide by 0. You still have some hedging against, you know, that you can exit the algorithm gracefully, yes.
The HPTVM.
That's the next talk,
Oh, okay.
time value of
All
money.
right, but I always use it as an example.
Yeah,
You have an initial guess. Now, one of the things that HP did was to figure out for their, you know, compound interest calculations was an effective initial guess that was going to work for, you know, the whole gamut of problems. Do you have any, maybe you covered?
no, because I mean, you could be solving almost and virtually infinite number of equations, and that would be very difficult, yes.
So
If you have a specific family of equations, yes, you can do that.
So the best guess would be done by somebody who is more mathematical familiar and make a good judgment for that.
Yeah, yes, yeah. It's a matter. It depends on the problem. Yeah. So. Okay. All right. Thank you.
Thank you, Namir.